Hello, good afternoon, everyone. Welcome to our Tuesday seminar. Today our speaker is Daniel Bratton. His talk is When the Scaling's Unbalanced.
Thank you. Good afternoon. I'm going to talk about a recent and ongoing program on anisotropic scaling invariance in quantum theory that I'm working on with people at the Technion. You can see from the sidebar I'm going to give you a brief review of scale invariance in physics before I tell you about my contributions to this area, where I'll focus on the breaking of continuous scale invariance down to an infinite discrete subgroup. Then I'll finish up with future directions, where I'll lay out a set of concrete problems that need to be solved to push this program further forwards. Okay, that said, let's get started. Okay, so we're often looking for limits of our models of nature where we can actually solve them. Okay, and one of the most successful sets of limits are the scale invariant limits. This is where all the relevant scales in your problem drop out. So let me demonstrate that by an example. Here we have the Dirac fermion in 4 dimensions. Now hopefully I don't need to convince you, but that when the energy is much, much larger than the mass, you can treat it as negligible. And the resultant equation is this. Okay? And this equation actually has a scale invariance. It's this scale invariance here, which I call the relativistic scale invariance. So if you scale time and space, you'll find the whole equation is invariant under it. And so you can actually use this to generate more solutions because the wave function also has to transform in the right way under scale invariance. Okay? So that's scale invariance at high energies. You can also find scale invariance at low energies. So here, this is a scalar field, a massive scalar field. I'm going to make it charged. I won't write down the conjugate. You just need to keep that in mind. And because it's charged, there's a global U1 number symmetry, and that will be important. Okay? So now you can ask yourself, what does this theory look like at very low energies, energies below the mass of the scalar? Well, you can intuit the answer. You're not going to be able to produce or destroy particles anymore, where here particles are labeled by that U1 global symmetry I just talked about. So you start off with a number of particles, you perform a scattering experiment, you end up with exactly the same number of particles. This is what makes non-relativistic field theory a much simpler theory to deal with. Okay? What does that mean at the level of the equation of motion? It means you take this equation, you perform this limit, you have to do certain things, and you get the Schrödinger equation. Okay? The Schrödinger equation is also scale invariant. But it's a different scale invariance to this relativistic equation because you need to transform time twice as fast as you transform space. Okay? Actually, just like this equation, the scale invariance is part of a much bigger group. This has an invariance under Schrödinger symmetry, which you can think of as one kind of non-relativistic conformal symmetry. Okay? But these are just examples that hint at something much greater. Okay? And this is the importance of scale invariance to the renormalisation group program. Okay?
Let me ask you.
Yes.
So the second one, for the low energy case,
yes.
compared to the mass scale, yeah?
Yes.
You cannot simply from that equation do this, right?
No, you have to redefine your, yes, I should have called this a separate symbol. You have to redefine your psi, and then you separate out.
This is a phase sort of. Like,
yes, exactly. You separate out a phase.
Okay.
Exactly. I didn't want to confuse people, but yes, you separate out a phase. Okay. Good. So as I was saying, this hints at something much, much deeper. So let me remind you, I think everyone in this room has done a course on quantum field theory. The idea is that when you perform a calculation in quantum field theory, you often find infinities. So you're forced to introduce a cutoff to regulate things. Now, working with a theory with a cutoff is not a bad thing. It's fine, you can do calculations, they might be wrong or right, but you can, work with it. But ideally what we'd like is a theory where the low energy observables don't depend on this arbitrarily introduced cutoff. So how do we see that for these renormalizable theories, we notice that our Lagrangians have many model-dependent parameters that up until this point in a quantum field theory course, we didn't worry about what their value was. Okay, but we should have done. So now we want to fix those values. So we go away, find some representative experiment, and we use that to define what the value will be. In doing that, we see that we can absorb the cutoff-dependent part of the calculation into a definition of the coupling. Okay? Well, at least in renormalizable theories, you can do this. So now your coupling depends on that cutoff or the cutoff or the observation scale. And you can ask, well, how does that coupling flow with changes in these objects? And out of that, you get the renormalization group flow equations. I'm highlighting this because it will be important later. Okay. And in particular, what you want to happen with your renormalization group flow is that you end up at a fixed point. What this means is that there is a single theory that governs the low energy dynamics of the theory you initially started with. Okay? But what's special about a fixed point is that the theory there must be scale invariant. Okay? That's the definition of a fixed point. You can break Lorentz symmetry, you can break rotation invariance, you can break any symmetry you like, but that endpoint has to be scale invariant for it to be a fixed point. Okay?
But there's an issue, yeah. If you look for the classically, yeah, you can look for the fixed point when you consider the renormalization group flow.
Yes. I'm going to move beyond classical in a minute and go to quantum.
I'm just wondering, if that fixed point is real fixed point, or if you consider quantum correction.
I will always work in quantum theory, so I just use these as an illustration of scale invariance. But I always work in a quantum theory.
Okay.
There are questions here. I'll come back to them in a minute. Okay, so here are the two scale transformations I talked about here. But there's a very obvious generalization, right? This goes under many names. I will variously use anisotropic or Lifshitz, depending on how I'm feeling from one moment to the next. But the point is that you allow time to scale with a different rate to how you scale space. This Z here is sometimes called the dynamical exponent. Okay? But quite legitimately, you might say, well, okay, you generalize, but so what? Where's the physics in that? And the answer is that there are actually systems, observed systems, where the symmetry occurs. So one class of examples, which I cite here, are the multi-critical points of certain materials. So you have many critical points, and for example, they meet in a triple point. And certain triple points will have this anisotropic scaling symmetry. Okay? And also strongly correlated systems, you can find this symmetry. So it does exist. It's something we should worry about or be interested in. More speculatively, you can, these symmetries actually might be relevant for particle physics and quantum gravity. In particle physics, what you find is if you have Lifshitz symmetry, some of the infinities that you get in quantum field theory become more tame and cease to be infinities. Because as long as Z's big enough, this grows more quickly. Okay? So that's the interest from the particle physics side, particularly in cosmology, where you might argue that at low energies you have relativistic invariance, but at high energies you have Lifshitz invariance, something else. Okay? In quantum gravity, there's a lot of work on this so-called Hojava gravity, which I'm most familiar with through the ADS-CFT correspondence, where you have spacetimes with different scalings in them to the usual ADS. So when you go to the boundary, you have a Lifshitz field theory rather than the usual conformal field theory. Okay? I'll give you all these references at the end. Okay? Good. But I'm sure it's not a surprise to anyone in this room that simply because I write down initially a theory that's scale invariant, when I actually do things with it, it might not be. Okay. So most of us are familiar with the quantum version of the statement, but let me just lay out the classical one as well. It's possible that, say you have a classical mechanics, it's quite possible that the Poisson algebra for the manifold you're on might not be able to represent a symmetry group. So this would be an example of a classical anomaly. They do exist. But as physicists, we're much more familiar with so-called quantum anomalies, where you start off with a classically invariant theory, but when you quantize, because of the way you have to regulate things, the symmetry is broken. Okay? So let me give you a very simple class of examples where scale invariance is broken from the classical. Here, this is a Dirac Hamiltonian. It's interacting with a Coulomb potential. Actually, this has been used in graphene, so it's an object of interest at the moment. And this is just the normal Schrödinger Hamiltonian interacting with a dipole potential. I've integrated out all the angular degrees of freedom. There's a very precise way to do this, so you just get a constant here rather than angle-dependent parts. Okay? So classically, these are scale invariant with relativistic and Galilean scale invariance, respectively. Okay? But if you want a quantum object, you have to make sure, if it's to be an observable, you have to make sure it's self-adjoint. And doing that, there's only a certain number of ways to make an object self-adjoint, and doing that actually can break the scale invariance. Okay. So that is an example of a quantum anomaly. You started off with a classically scale invariant theory, you quantized it, and broke the scale invariance. Okay? And what happens when you break that scale invariance depends very much on this coupling lambda. Okay. For lambda small, you find that you get one or two bound states, or at least a finite number of bound states. Okay. Actually, for these you get one. I think you get one bound state. But it's at non-zero energy. So at low energy, your theory still looks scale invariant. Okay, because you just make sure you're below the energy where this bound state is. Okay. However, as you increase lambda, what happens is you find a tower of energy states appears, rather than just the single state we had here. Now, I've given an expression here, n belongs to z. So you can see as n gets very large, this is going to go to 0. The E here is negative. So 0 energy is at the top of the tower, but it also goes down all the way to minus infinity. Okay. So this is a manifestation of a residual symmetry that's left over after you've broken the continuous scale symmetry.
So the n can take a negative value too. What is it? The positive or?
Yes, positive or negative. It can go all the way down to negative infinity. Yes. So it's okay. Yeah. So this is an example of a leftover of a consequence of a leftover part of the continuous scaling symmetry. This gets called discrete scale invariance, and you can check everything is invariant under this transformation. Okay, when you scale the coordinates by a particular scaling, or multiple powers of it. Okay. Most interesting for us, and this will come out again later, is that this means there is a quantum critical phase transition in these systems. You start off with what at low energies is a scale invariant theory, and then as you tune up your coupling, you end up with a theory that is not scale invariant. It's discrete scale invariant with an infinite number of states clustered around 0 energy. Okay?
Sorry.
Yes.
Hamiltonian, Dirac
Yes.
Hamiltonian is Lorentz invariant.
Mm-hmm. Yes, it's Lorentz invariant.
What's the meaning of R? It's just
Oh, it's, well, okay, I'm going to break translation invariance by having an origin. But yes, it's still got, like, the rotations. It comes from a Lorentz invariant. So,
Or if you write that R probably or not.
yeah, I
Not only the translation, if the Lorentz boost does not.
yes, I'm the Lorentz boost, sorry. So, ignore this for a second, set lambda to 0, then it's Lorentz invariant. Okay. That's what I meant by this Lorentz invariant, yeah. But we're going to turn on a background potential, which obviously picks an origin and breaks a lot of these symmetries. Okay. Yes, you're quite right. And actually, thank you. You've reminded me of something I wanted to say. So this system, so this breaking of continuous scale invariance to discrete scale invariance has been known for this system for a very long time. It's the Efimov effect. It's very important for nuclear physics. Okay. This was not known until very recently with experiments in graphene. And actually my collaborators are some of the people who showed that this transition occurs. That you get this infinite tower of states with geometric spacing. Okay. I think that was...
So here, when you use this, you only concern about the scaling invariance?
Yes.
Okay.
Yeah. Well, yeah, I'm going to turn on various potentials that will have an origin, so they will break the rest of the symmetry.
I think I'm just wondering, you use this kind of Coulomb type potential. Is that not a... It's not consistent with the relativistic picture, do you?
How do you mean?
You say since the relativistic, but the potential to project is action at distance, right?
Yes. So I should be more careful, you're quite right.
Yeah.
When I refer to relativistic, I mean just this part. And when I refer to relativistic scale invariance, that doesn't mean you have the Lorentz group. It just means, time and space scale at the same rate. I couldn't find a better name for it, but maybe there is one. Okay, so that's the past. Okay. This is the present. Okay. So I began by asking myself some questions. The first question is, why was there such a small set of these systems with a quantum critical phase transition? Up until this year, there were 2 systems known. Part of my work was to show that there are more than 2 systems by generalizing the scale invariance from this relativistic and Galilean form to anisotropic scale invariance. Okay, so we had an answer to this question. There's more than 2. There's an infinite number. Okay. You might also ask, what are the conditions on these systems for this transition to occur? I also have an answer to that question. It's all going to depend on the zero energy modes. I'll explain how later on, but that's something to keep in mind. And finally, you can ask, well, okay, you found this very interesting phenomenon, but where is it? What do I go and look for to tell in my system that this is happening? I have 2 answers here, and part of my future program is to find more, but you can look at the energy levels and you'll see geometric towers. Or you can actually perform a renormalisation group analysis, and you'll see the appearance of limit cycles. I'll explain what I mean by a limit cycle as well in a bit. So my program was to generalize these systems, these Hamiltonian systems, to more generic things with just general scale invariance in quantum mechanics. And in future, what I'd like to do is extend this into field theory and find examples in field theory of this discrete scale invariance. There's 1 or 2 already known, which I'll point out as we go through. Okay, good. So now we're on to my work. So my first success in this program came from considering Hamiltonians of this form. So here we have the kinetic term. It's just p to the 2n. And here we have a potential. Now you might worry that there's a derivative here, but I can assure you that you can get that derivative by gauging your theory. So you have some, you can shift p to p plus a, so you have some background gauge field. And just like in 2 dimensions, you have magnetic monopoles. You can generate these derivative interactions.
So the d stands for derivative?
This d is the derivative with respect to r, yes.
Oh, okay.
Okay, so I'm assuming spherical symmetry.
Powers, okay.
Yeah, indeed. So this has a nice scale invariance, okay, at least classically. But this is very divergent. This is badly divergent as r goes to 0, okay, particularly the potential term. Now, if I told you that I had a divergence in quantum field theory, you'd know exactly what to do. You'd introduce a cutoff, calculate with the cutoff, and then see whether any of the results depend on that cutoff. Okay? So I'm going to introduce a cutoff at r equal to L to regulate these infinities. In particular, I'm going to introduce a hard cutoff. So I'm going to assume that the probability current vanishes on this cutoff here. What's the physical interpretation of that? That means that the only way that physics here can depend on this cutoff region is through the boundary conditions. There's no flow of particles across this cutoff. Okay? Good.
So effectively, you just put an infinite high
Yes.
barrier there.
It's an infinitely high barrier. Right. Yes, and then we'll vary to see how the results depend on this. Okay. So what I said to do here is to set the probability current to 0. Okay. So hopefully you will remember what a bilinear form is. I'm looking at the students. So what you need to do is take the probability current, and it's a theorem that you can take any bilinear form and eventually write it in new coordinates as a diagonal matrix with 1s, -1s, and 0s along the diagonal. Okay? In these cases, you just get 1s and -1s, and in fact, what happens is your bilinear form will eventually assume this form. Okay, that's your current J. And we want to set that to 0 in a non-trivial way. Okay. So we can trivially set it to 0 by setting, these depend on the wave function and all the derivatives at the cutoff. We can trivially set it to 0 by setting the wave function and all the derivatives to 0. That's the wrong thing to do. That will make your Hamiltonian non-self-adjoint. But if you find the non-trivial solutions to this, your Hamiltonian will be self-adjoint. In fact, all the non-trivial solutions are of this form. So you've introduced a whole new set of model-dependent parameters to play with. These are the unitary matrices, UN. And there are n of them. I would remind you that the derivative here came with a 2n. So for 2n, there's a UN matrix. Okay? Actually, it's a bit of a shame that more physicists aren't sort of happy with playing around with self-adjoint extensions, because they give you a whole new extra handle on your quantum mechanical models that you didn't have in the first place. But I will admit that a lot of the literature is very mathematical, so it's not easy to deal with. So this probability current is a nice recipe to deal with it.
Sorry, I forgot what's the meaning of psi plus.
Okay, yes. So psi plus, I diagonalize this probability current. So the probability current is going to depend on the wave function and 2n minus 1 of its derivatives. So the first derivative, the second derivative, all the way up to the 2n minus 1th derivative.
What's the meaning of the plus?
Okay, yeah, okay. So the point is that the plus, so I said you can diagonalize this probability current, and you diagonalize it into this form. So the plus refers to something with a +1 here, and the minus refers to something with a minus here.
Oh, I see.
Okay. But they're just linear combinations of the wave function and its derivatives. Okay, at the cutoff. Okay, good. So this was work that we put out in June. And we basically spend a lot of our time computing the energy levels. Okay, so here's actually an example. So here's the Hamiltonian. This is the epsilon to the 4 here is the energy. Okay? So I'm plotting the energy against the cutoff. This axis is a bit funny. I blame my collaborator for choosing this because he liked this way around. Up here is 0 energy. Down here is negative infinite energy. Okay? And you can see, right, so focus on this region first. You can see for small cutoff, small values of the coupling, there's a single state in the spectrum, only one. Okay. So as long as your energy is below that state, it's scale invariant. But at some critical coupling, an infinite number of states appears from 0 energy. They come out of 0 energy. Okay? I should say this is the boundary condition here. They come out of 0 energy. And you can go away and do this calculation yourself, and you'll find that the spacing between these, so we draw a line like this, is constant. You can see why that is. by taking the logarithm of this. So you have log E is some constant, log E 0, minus 2 pi nu times n. Okay? So the spacing between the energy levels is 2 pi nu. It's a constant value.
Question, yeah.
Yes?
If the coupling is bigger than the critical one,
Uh-huh.
then the system will have the infinite many of the energy level with no lower bound. Right.
When you take the cutoff to 0, there will be no lower bound.
Yeah, in that case, the system becomes unstable, right?
Good. So you've actually preempted.
It's not well defined in that case.
Right, exactly. So very good. you preempted a future question.
Okay.
Yes, that was something that worried me. So as long as you have a cutoff, there's no problem. And you can treat that system just fine. There's some physics in the core region that you rewrite in terms of these model-dependent parameters, and you don't worry about. That will be fine. But if you take the cutoff to 0, yes, you're right. There's an infinite number of negative energy states. And that will be this question here about stability, where I'm going to use supersymmetry to fix that problem. Okay. Good. Okay, good. So yes, what did I want to say here? I think I've covered everything here. So you can see there's a geometric tower. Okay, I will tell you how to determine which Hamiltonians have this geometric tower in a moment. I want to give you some other phenomena that are a consequence of this discrete scale invariance before I tell you what the diagnostic is. Okay? So I mentioned the renormalisation group earlier. Let's have a look at this. Okay. So this starts with asking yourself a very simple question. Let's say I have some cutoff and I have some state. Now I want to some reference state with some energy. Now I want to move that cutoff down. I want to scale that cutoff. Okay? So now the state has a new piece in this region I've generated. If I want the state to have the same energy, then my boundary condition on the new cutoff is going to be different to the boundary condition on the original cutoff. Okay? And as a question, how do you have to change that boundary condition to keep that state at the same energy and in your spectrum? Okay, so now we let our parameter depend on the cutoff. Should be very familiar from field theory, right? And you can perform this transformation and you come up with this equation here. Okay, so I don't want to give the explicit forms of the C because they're a bit complicated, but they're easy to find. You just take your Hamiltonian, you rewrite it as a set of coupled, linear, first-order differential equations, and then the matrix that you get from that is just the C's. Okay, okay, good. So this tells you how UN has to change to keep psi at the same energy. Okay? But something very special happens when you consider low energies and low cutoffs. Then all the energy dependence of this equation drops out. So it doesn't matter what reference state you started off with. Okay? And in that sense, it's a renormalisation group flow equation. Because it doesn't matter what state you consider, it tells you how the boundary condition has to change to keep all the states at low energy at approximately the same energy. Okay? Actually, these equations are rather nice. They're called non-symmetric algebraic Riccati equations. They're fun to play with. And there are methods which I won't go into for determining what the fixed points are. We use them in the paper that's going to come out next month, but I won't go into them here. Okay? But I should also say we're not the first people to consider the RG flow of these boundary conditions. There are some references here. But in their cases, they only have ever had to deal with the U1, so it's a much simpler equation. When you have the matrix equation, you can't use the simple things that you could in the U1 case. Okay, good. So we've got this RG flow equation. Let's analyze what happens as we change the cutoff. Okay, so now I need to remind you of a little bit of history, going all the way back to Kenneth Wilson's papers on the renormalisation group. There are many ways that a renormalisation, well, sorry, I keep saying many. There are 4 ways, that's many depending on your definition of many, in which a renormalisation group flow can end. One we're very familiar with. That's a fixed point. Okay? They're good. Another which we don't really see very often, I think maybe at all, but people at least know what I mean, is chaos. Okay? But there are another two that people are less familiar with, the limit cycle and the limit torus. Okay. So let me explain what a limit cycle is first. So a limit cycle is where you have an RG flow, and eventually it ends up on a one-dimensional subspace of your RG space, repeating the same trajectory over and over and over again. So it's topologically S1. Okay? A limit torus is a case where you have, so the limit cycle, there's one period, okay, as you go around this S1. For a limit torus, you have multiple periods, so it actually describes a much bigger subspace of the space of RG parameters. Okay?
But
Yes.
I thought with the renormalisation group, you can also go to like a strongly coupled theory or a symptomatically free.
But they would be, well, the strongly coupled would be a fixed point, right? And then you have the Gaussian fixed point, which is the free.
So you classified that as...
I would call them all fixed points. We can go into the various gradations of what fixed point is, but I would classify all of those as fixed points. At least for
there's an issue. For example, if you go from weak, normally you can write on a series in weak coupling. But when you run, if the coupling becomes strong, the series is invalid anymore. So how can you do that before you hit the fixed point? You only have the limited knowledge of the theory.
Well, in this case, all the RG equations are exact. So you know,
But how do you
it's not a perturbation theory.
I know it's not a perturbation theory, but you begin, for example, you begin with a perturbation theory. The equation established is simply from there. When, for example, when the coupling runs, if the theory changes,
Well, I mean,
from a weak to
well, in this case, it's not a quantum field. So yes, if you were talking about quantum field theory, this is something you'd have to consider. But this is a quantum mechanical theory at the moment. So the couplings are fixed. In fact, the couplings in my Hamiltonians satisfy trivial beta functions because they're scale invariant.
Okay, the one you just mentioned about this kind of ending, yeah. Fixed point is we understand.
Yes.
If two cares, that means the bifurcation, right?
Right.
But in that case, we still call it as the ending because the runs, then we can have different
Right.
choice.
Yeah, so it doesn't as you scale, it just continues to fill up the space, right? It doesn't go anywhere. Well, actually, it makes this strange attractor shape. It doesn't stop anywhere, unlike a fixed point, which ends.
Yeah.
Same with the limit cycle. It doesn't stop
Exactly,
anywhere.
yeah, so you still say that's the ending.
Well, yeah, that's the ending. It's the behavior that. Sure. Okay.
Anyway, I don't know. Yeah.
It's the behavior that the equation, the solution to the equation
you can
tends
say ending
to.
on a line and ending on a torus.
Okay. Oh, okay. Yeah. Well.
Okay, man.
Yeah. Okay. I take your point. Okay. So, where was I? Okay. There are many ways for it to end. So, in recent work, we analyzed a much larger class of Hamiltonians. Again, scale invariant, spherically symmetric, and looked at this RG flow equation to see where we ended up. And you can get three of those behaviors that I mentioned. You can get fixed points, you can get limit cycles, and you can get a limit torus. Okay? And the physics is different for each one. Okay? We know what happens with a fixed point. Okay? With a limit cycle, this is actually, again, we're not the first to note this, but this is, if you have a limit cycle, you know you're going to have discrete scale invariance. The limit cycle implies the existence of discrete scale invariance. I'll tell you why a bit later. Right. But what's different to this previous work is that we have the first examples of isolated limit cycles. What do I mean by that? So this Hamiltonian here, the one that's been most studied, does have limit cycles when lambda is large enough, when you're in this DSI regime. But every point on the trajectory, every point in the space is on a limit cycle. So the space is actually filled by multiple limit cycles. Here's an example of 2 limit cycles. Okay? That's a non-isolated limit cycle. An isolated limit cycle is where there is one or maybe a few limit cycles in the space, and wherever you start, you end up on this limit cycle. Okay? And here's an example from our paper, our soon-to-be published paper. Okay. We also found some other interesting miscellaneous pieces. So for our generic scale-invariant Hamiltonians, you can have multiple geometric towers, not just one. So these geometric towers differ in the choice of zero energy here. Okay? The reference energy, not zero energy. And we found you can have limit tori. So we have flows where some subspace of the full space of RG parameters is filled up, okay, with two or more periods. Okay? And then we also know that the energy spectra for a limit torus is very close to the energy spectra for a limit cycle. So if you have 2 periods, you can imagine deforming one of those periods until those periods match. Then that's a limit cycle. So the energy levels of the limit torus, you can guess what they're going to be from a nearby limit cycle. And there are just small perturbations around those values. But there's no discrete scale invariance in this case. Okay. Good. So that was all at finite cutoff. What about zero cutoff? Oh, wow. Okay. What about zero cutoff? Okay. So this table refers to this set of Hamiltonians. Okay. Now with zero cutoff, things become a little more complicated, because if you look at the behavior of the wave functions that solve this Hamiltonian at zero cutoff, they have these power law behaviors. And you better make sure that this doesn't diverge too quickly at r equals 0. If it diverges too quickly, you need to remove that solution from the space of allowed solutions, because it's not normalizable. Okay? So, I mean, here was the Schrödinger Hamiltonian we started off with. So when lambda is below this value, you have a U1. Above this value, you have a U1. And when it's below this value, it's essentially self-adjoint. There's one set of boundary conditions you could pick. Okay? This is an n equals 2 case, and here you can see a change in the allowed space of boundary conditions. So U1 for this, a U2 for this. So some of the modes that were allowed here are no longer allowed here. And eventually, as you get lambda low enough, you always reach an essentially self-adjoint object. And here's the n equals 3 too. These were precise, whereas this is approximate. Okay, so that's what happens at zero cutoff. You get these same sorts of behaviors. It's just the boundary condition parameter. It's not necessarily a UN. It can be smaller. Okay. Now to the interesting part. I'm going to link the zero energy modes to the existence of discrete scale invariance. They will be a diagnostic. So all you have to do is solve your Hamiltonian for the zero energy modes, which are just power laws, and then you know whether you're going to have discrete scale invariance or not. How does this work? So as I said, a low energy, you have power laws, and there's a constraint on these power laws for the Hamiltonian to be self-adjoint. Okay? So this is here a generic low energy wave function. These are some constants. And this here is the modulus of the energy to some root. Think of it as the energy. Okay. So if you examine this wave function for a moment, you'll see that there's a very special set of differences. That's when this is purely imaginary. Okay? So that's when delta I and delta I plus n all have the same real part of n minus a half. This becomes purely imaginary. For everything else, this is positive. So when you're in the ultra low energy regime, only the imaginary powers, the things with purely imaginary powers will remain. Because anything with a real power falls off quicker, right? Okay. So this is oscillatory in the energy. And it's that oscillatory behavior that is responsible for DSI, because you can scale this object, and you just end up with a phase. Okay. But you have...
You just say the presence of zero modes is just an indication of your
I'm saying you can use the zero modes as the diagnostic.
diagnostic.
So you compute the zero modes, which are just these power laws.
Yeah.
And then if you see that any two of your power laws have a difference that's purely imaginary, you have discrete scale invariance. That's all you need to check.
Oh, say again, sorry.
Okay, sure. So you solve your Hamiltonian at zero energy for the power laws. And then you ask, well, is the difference of any of these powers purely imaginary?
Purely imaginary.
If the answer to that question is yes, you have discrete scale invariance.
Why?
Why? Because if you look here, this is the low energy wave function, right?
Okay.
So let this be, let's say there's only one pair whose difference is imaginary.
Yeah.
This is now purely oscillatory.
Pure what?
It oscillates.
Oscillating.
Yes. So just like cos and sine, it has a period.
Okay.
And that period is exactly the difference in the energy levels. So that's why when the difference between any of the roots is purely imaginary, you have discrete scale invariance. And now you can do all kinds of more interesting things, like, so I can engineer my Hamiltonian to have arbitrary values of the power laws, so long as this constraint is obeyed. Okay? So you can have, let's call the line n minus a half the symmetry line. So notice when the difference is purely imaginary, it must have real part n minus a half. Okay. So I can arrange for multiple imaginary differences if I want, just by engineering my Hamiltonian. If they have a rational ratio, you're going to have a limit cycle. If not all of their ratios is rational, you can have a limit torus, because there are multiple distinct oscillations. If there's one period, you have a limit cycle. If there are multiple periods, then this is going to be quasi-periodic. You have a limit torus. Okay? I think I actually summarized that in this table. So just by looking at the zero modes, you can determine what you're going to get. So let me just go through this quickly. Okay. If all the roots are on the symmetry line, and their ratio belongs to the rationals, you have many limit cycles. Okay, so this is the non-isolated limit cycle case. If it's not rational, you have limit tori. Okay? If you have some roots off the symmetry line, you can have rational differences for roots on the symmetry line, rational ratios. You're going to have isolated limit cycles. If some of the ratios aren't rational, you can have an isolated limit torus. And then finally, if none of the roots are on the symmetry line, you have two n fixed points, only one of which is stable. Okay? So this is behind my statement: the presence of discrete scale invariance can be determined purely from the zero modes. Okay?
So only one. What's the data? The data, what's that represent? Just like the wave function, just like.
Yeah, you just get the power law.
Yeah, the power, yeah.
And then you ask, right, okay.
Basically, the power you have, if it's real, then you don't have the discrete.
Yes, if it's real, you have fixed points.
Okay.
If there are imaginary parts, you can have any of these behaviors depending on what the ratios of those imaginary parts are.
Okay, yeah, you have to, yeah.
Again, all down to this oscillatory behavior.
Yeah.
Okay, good. Right, so I think I can make the strong claim that the breaking of continuous scale invariance to discrete scale invariance is a generic feature of scale invariant quantum theory. Okay?
Do you have the feeling, what's the physics behind? First, you need to have 0 modes. Then you have to have in addition the power has to be complex. Then you have the difference. The difference has to be
right.
Yeah.
So
what's the physics?
what's the physics?
Is there anything?
The existence of the power laws follows from the fact you have scale invariance, right?
Yeah. Okay.
So that's that thing. Tick. What about you needing imaginary parts?
Yeah. You first you have to have 0 modes.
Yes. Well, again, the 0 modes follow from scale invariance.
Okay, scale invariance. Yeah.
Yeah.
You're right.
I mean, at the moment, I don't know if there's anything deeper than that the wave function, at the moment anyway, that the wave function is oscillatory at low energies. I mean, that's the physics, right? The wave function is but it's not so satisfying because that's a mathematical statement.
Yeah.
I prefer something a bit more physical, but maybe in the future.
Okay.
Okay, good. So that's all old work. One paper was published in June, another one's coming out this coming month. Okay, but now let's talk about the concrete problems that are left to solve, one of which you already pointed out. These systems are fundamentally unstable at 0 cutoff because you have a state of infinite negative energy. If you have a cutoff, it's not a problem. But I worry about these things because I'm a theorist. Okay, so this was the Schrödinger Hamiltonian I started off with. We can start with a cutoff and then take that cutoff to 0. As you said, it's dynamically unstable. But if you stare at this for a moment, you'll realize, hang on, if I squared this Hamiltonian, all my energies would be positive. Okay? So now they cluster from above down to 0 energy. I've written it here. The reason I call this as a partial solution is, yes, this is a fine Hamiltonian in the space of scale invariant Hamiltonians, but it's not very satisfying.
But in that case, your n can only take you don't have to do the infinity, but that's okay. Yeah, sure.
It's stable. It's stable.
Yeah, I'm just wondering because if the energy blow up, that's okay.
Yeah, it's a positive infinity. So. Okay. But this should remind you of something. There's a case we're very familiar with where the Hamiltonian is the square of something. And that's a supercharge. Okay. So I've worked on this a bit already. And this gives a good reason to consider these Hamiltonians, these square Hamiltonians, because now you want to conserve your supercharge. So that's a good physical reason to consider things like this. And we know straight off that as long as the supercharge is self-adjoint, everything's going to be okay. The difficulty is in making the supercharge self-adjoint. I should say there's a theorem which tells you the square of a self-adjoint operator is self-adjoint. Okay? At the moment I've been looking at...
Okay.
Please.
Okay, I'm just, you say the Q, okay, you still have the anti-community with each other, Q plus, Q minus.
Well, that's also a problem, you see, because you need both of these separately to be self-adjoint.
Yeah.
So that their product is well defined. And that actually reduces the number of allowed boundary conditions very strongly. There's work on this already by a guy called Falomir and collaborators. But again, they only focused on the Schrödinger case. Okay. So the current status is that I've already figured out what the self-adjoint boundary conditions are for these Q. They're big, as you'd expect. It's a bigger allowed class than the simple Schrödinger case we started off with. And the upshot is, one of the upshots is that whenever you have DSI at negative energies, you can't factorize the Hamiltonian. It's just some algebraic observation. So DSI at negative energies is incompatible with SUSY. But DSI at positive energies, so you take your Hamiltonian with discrete scale invariance, you square it, DSI at positive energies is compatible with SUSY. Obviously, because SUSY should have a lower bound, right, of 0. Actually, what's very nice, and I haven't quite figured out how to connect the two yet, is that these are higher derivative superchargers. So they have higher derivatives of the radius. And there's a big sort of body of literature on something called polynomial SUSY, where they also look at these higher derivative superchargers. And here, your anti-commutator, rather than just being the Hamiltonian, is some polynomial of the Hamiltonian. But this is very speculative as to whether they're connected yet. Good.
If what you said turns out to be true, that means the previous solved one only have BPS configuration, because that means the co-plus acting on the state vanishes.
Right.
Right.
Yes.
That's basically say you preserve, and it's the from what if you co-plus command, that means preserve half of SUSY. All this configuration you consider preserve half of SUSY.
That's an interesting point.
Then I think here probably there's an interesting point, because we know that you have topological reason, because that's the zero modes.
Yes. Right, you can change the parameters, right, and because of the written.
Because all the states you consider just zero modes part.
Yes.
From the new theory point.
Yes.
I don't know if this has anything with the kind of Wheaton's.
Yeah, so the written index for these things is a little bit different, because you can have a space of zero modes, and then things get a bit more complicated.
Okay.
But if you go to this reference, which again I'll give at the end,
okay.
there's a long discussion about this. This is actually a review. Okay, so that's one problem with a very concrete thing to do. Here's another question you might ask. So this is a step towards putting these things in field theory and looking for DSI in field theory. What you can do is couple. So when the gauge field is zero, you get the zero potential Hamiltonian that I've been working with out of these. A way to get the potential that you want is to couple to an external gauge field. Okay. In particular, you want an electric multipole moment, the right electric multipole moment, and then you'll have DSI. Okay. But that's very unsatisfying. It would be better if the discrete scale invariance happened as a consequence of just the anomaly, that you got the right potential. So there's already been some observations again for the Schrödinger system. This is Oren Bergman's PhD thesis, where they talk about the Aronoff-Bohm effect. And that's a way to generate the right potential just by just from the field theory, without having to put it in externally. So this is something I would like to look at. The calculation here is to compute the Aronoff-Bohm effect and make sure that this field theory is... You need to add another term to make the field theory perturbatively give you the right answer. Again, I'll refer you to Oren's work. It's very readable. And there are multiple extensions with non-abelian gauge fields. This Aronoff-Bohm effect in 2 dimensions is exactly the same as the scattering of anyons. And then you might ask, well, okay, does this quantum critical phase transition compete with anionic superfluidity? Which one wins out? Do you have an anion superfluid or something different? And there's a hope, I hope, this is a bit of a long shot, but I can identify the field theory anomaly coefficients that are responsible for DSI, in these systems. Another possible way to go, I'm running out of time, is to look at the thermal partition functions and calculate thermal corrections. So this is particularly interesting because there's a large set of very interesting systems where at 0 temperature you have a quantum critical phase transition. But then as you raise the temperature, there's a new region of behavior you didn't expect. Okay, so here there would be some material that's approximately scale invariant at low energies. Here it has discrete scale invariance at low energies. And this could be an indication of some new type of material you didn't think of before. I mean, this is exactly what happens with strange metals. Okay, by the way, I'm not saying that this is a strange metal, I'm saying that this is what happens in that case. In fact, quite interestingly, I didn't mention it earlier. I'll mention it now. So the appearance of DSI is associated with a UV and an IR fixed point annihilating. So you lose the fixed point. Okay? And that gives a BKT-like transition for those of you who are familiar with BKT. It has been suggested that this might be responsible for the transition in QED3. So QED3, for the students, is a very interesting theory because it's strongly coupled, which you wouldn't expect. And people aren't sure, as you tune the number of flavors, people aren't sure when there's a transition between a chiral phase and I forget what the other phase is. Does anyone remember? Anyway, there's a transition. But there have been multiple attempts to calculate this value, and each of them seems to give a different answer. There's 0, there's it never happens, there's somewhere between 3 and 4, and it's been argued that maybe this fixed point annihilation is responsible for this phase transition in QED3. So this has maybe some interest in other areas. Okay, and finally, you could also compute, because you're working now with a field theory, you could compute correction to the critical coupling, which will give you these lines as a function of temperature. That's quite interesting too. We also can ask about discrete scale invariance in gravity. There have been some works already. So in holography, there's been a consideration of Lifshitz anions. There's also a holographic model of the Efimov effect. And yeah, these things are all sort of tied up in non-relativistic conformal field theories. So let me give you an example. A well-known case of holography, you can think of it this way. Okay, so you have some relativistic equation that you write in light cone coordinates. Then you compactify one of these light cone directions. Okay, so now your field is going to have a decomposition into modes around this compactified light cone direction, and the result is the Schrödinger equation. Okay, you essentially do this process in the space-time, dual to a conformal field theory, and you get a non-relativistic conformal field theory. So I have a question: what if you do the same thing for a Lifshitz space-time? Okay, take one of the light cone directions, compactify it. All that's going to happen is you'll have a higher derivative here.
Question.
Yes.
Yeah. If you go to non-relativistic case, what's the meaning of the light cone? The light cone has to be relativistic. If you go to non-relativistic, the meaning of light cone is...
In Lifshitz theories, you still have a light cone. They just sort of open and close a bit, depending on what direction your Z goes.
I think in Lifshitz theory, there's many confusions there.
Yeah, okay.
Yeah,
well, I mean, you're compactifying a light cone direction, so...
If you really go to the Lifshitz case, then you don't have this kind of light cone anymore, because basically that's just your non-relativity. That's just the pure space and pure time, because time now is absolute. Right.
I mean, well, at least on the level of the equation of motion, you can do this process. This is well defined.
Yeah.
But whether it's well defined, I think it's well defined.
Yeah.
That's why I saved this slide and towards the end, because it's very speculative.
Okay.
Similar question.
Yes.
In this case, what's the conformal group for the non-relativistic case? Conformal group.
Of the Lifshitz?
Yeah. What is this?
If you haven't answered that question, I'd love to hear it.
We are considering conformal CFT. Yeah.
Right. So
I wonder.
me too. Me too. I mean, I always save my very speculative slides to last, because people always have these kinds of questions, and they're good. I don't know. That's why it's interesting, at least to me. Maybe it's not interesting to others. I would say that these would be very easy to thermalize as well if you have a holographic dual, but I mean, this is incredibly speculative, whether you can do this. And less speculative but maybe less appealing to high-energy physicists, but more appealing to condensed matter theorists, is to consider fractional powers, the fractional Schrödinger equation, rather than these integer powers. These are particularly nice because this equation is inherently non-local. Okay? That's what the fractional derivative gives you. You can expand it in powers of derivatives. So it would be a very strong test to see this, whether the CSI to DSI transition is still associated with the zero modes, whether it still is associated with limit cycles. In these cases, that would be a very strong test of how powerful these observations are. In fact, again, you can find these things, these have physical uses. So when you have a condensed matter system, you can have a band structure that the mass of your particle can depend on the wavelength.
But in this case, the Hamiltonian, I don't know if it's even safer to join.
Neither do I. I would have to check. I mean, people have worked on the Bohr atom and things like this.
Yeah, that's a big issue, yeah.
Yeah, but people don't, I don't know how careful people have been with checking this alpha joint. Again, this is the last speculative slide. Okay, so to do this, there's a definite way forward. I could attempt to generalize my very general solutions to the integer equations of motion, but that's hard. I have some ideas, but that's hard. There's also this approach where it's called multifractional spacetime. So you replace, the key thing to do is replace the measure in your integrands by something that is smooth as you change the dimension. And I've given a reference here. There are people very interested in this thing. It's what they call dimensional flow, because there's an idea that maybe in high energies, gravity has a different dimension to how it does at low energies. But this is not something I'm very familiar with at the moment, but I know someone who's interested in it, and we might be working on something in the future. Okay, good. So let me summarize. I'm sorry, I'm 5 minutes over. So we've demonstrated the existence of this transition in a huge, infinite set of examples, and found the first application of isolated limit cycles in quantum theory. We've also shown that the property, whether this discrete scaling invariance occurs and whether this transition occurs, can be completely determined from the zero modes of the Hamiltonian. And we've also suggested multiple avenues to push this project forward, and they're all very concrete things to do. It's not like there's a mystery, except for the last two. Yes. Okay. So I would like to say thank you very much for listening. If you want the references, go here.
So two questions. First one is where does the potential comes from? From dipole or something?
Oh, right. So we're going all the way. Okay.
Yeah.
Well, there are multiple ways. Okay. So let's do the way that I think you'll be most happy with first. So if you vary this, you're going to get the Hamiltonian, okay, coupled to some gauge fields, okay. This gauge field, if you pick a background gauge field with the right electric multipole moment, it's very easy to generate in one dimension this Hamiltonian. Very easy. In higher dimensions, you're going to get intermediate terms. Okay? You can also get the derivative interactions. I was talking about D equals 2 earlier in anyons, by having a monopole. This just shifts. Okay. Let me rub this off. If you start off with the free Hamiltonian, and couple it to a monopole, you can see that you're going to get lots of derivative terms, intermediate derivative terms. And I would separate them out and call them the potential. Okay. Yeah, so there is one way to get it. is to couple to a gauge field. And actually, in the original paper that we wrote, my condensed matter colleague was very concerned about this. So we found a model where people look at a Lifshitz scalar coupled to a Lifshitz gauge field. So you don't have the Lifshitz gauge field treats space and time differently, but you can write something down.
So yeah. Oh, I understand. So
Great.
the second question is, can you give me an example for your model? I mean, for some real system.
Good question. The honest answer is not yet.
Yeah.
Not yet, but
A realistic system? What do you mean?
No.
like some experiment I can go and do in the lab.
What do you mean by realistic system?
I mean, maybe you can find this phase transition in some experiment.
Yeah, I agree. So, well, I can cheat, okay? And I can tell you that these, which are examples, have already been seen in real systems. You know, so this is just the Efimov effect, you know, in nuclear theory, and this was seen in graphene. But that's not really what you want. You want things with higher n. But I'm not an experimentalist, but it doesn't seem that hard to be able to do. But, you know, as theorists often have these notions that, oh, this is an easy experiment to do, and then you actually go to an experimentalist and they'll tell you.
For example, how to see what kind of quantity you can detect this kind of quantity continuously discrete.
Right, good.
The
So,
only thing you see before you have just a few bound states.
right. And then you'll have a lot of bound states at incredibly low energies, going up to zero. So,
Experimentally, you cannot do that.
right, so, well, I mean, you could do a scattering experiment and see, right, that there are low energy modes.
But the issue is once the things become this, from the lambda bigger than the critical dimension, the
Yes.
system will be unstable anymore.
Sorry?
The system will become unstable.
Well, except when there's a cutoff. So
The cutoff, that's just theoretically.
well, I'm not sure.
Experimentally, yeah, sure, but certainly we have the system, yeah.
Experimentally, it can be, you can have something that looks like this at low energies, but at higher energies it's different. And then because all these states are clustered around zero energy, it doesn't matter. But that's actually a good point, and part of the reason why I'm interested in these thermal things, because I want more diagnostics. I want to be able to say, go and look and you'll see this critical exponent, maybe, again, critical exponent.
In low energy, I see the Hamiltonian is like what you wrote down.
Yes.
The high energy could be completely different.
Yeah, so, I mean, the results I have, so we introduced a cutoff. The results I have are independent of what you stick here.
Yeah.
Doesn't matter. And as the energy gets low, you know, the system's not going to see this region anymore, right? As you look at longer and longer wavelengths,
Okay.
this is small compared to that long wavelength of observation. So it doesn't matter. Which is very cute.
So you say in that case, the system still be okay?
Yeah.
Okay.
Yeah. And actually, I mean, again,
The reason you have this kind of infinity negative energy is because you just extrapolate the potential use to the region. It could be.
yeah,
It could be very different.
yeah, we don't, I mean, I don't know what your image of a realistic potential is, but I don't,
So our next system work okay. That's usually fine.
yeah, I'm imagining something like this, you know. So as long as you're outside there, it looks like 1 over r squared.
Okay.
And then you can, you know, at low energies, this is not going to matter what happens here.
Okay.
Right.
Yeah. You only care about this.
Yeah, you only care about infinity.
Okay. So that's not so good.
I hope so.
In that case, you could see you could see some, if it's the sitting, yeah, you may see this kind of thing.
Yeah. I mean, again, in my theoretician's head, my idea is to take a system with a Lifshitz critical point with charged particles, and then just turn on some external electric multipole, which you can arrange. Now, again, that's my theorist's interpretation of an experiment, and that might be impossible to do, but in principle, that's something you could do.
Yeah, you basically see, if you see the energy level, the states, the number of states, when you change the coupling constant, if the number of states increases rapidly, that's maybe an indication.
Right, yeah. Well, and it's because so many states are clustered around zero energy, it's almost like you have a band, right? A continuous band.
Yeah.
I was thinking about this yesterday, actually. It's a nice way to get something like band structure without having to have an infinite number of particles. You know, yeah. In that sense, it's very cute.
If not, that's fine.
Thank you.
So,